Hello, good evening. Welcome to the 8th video in this series, and the first focusing on derivatives. It's another Let's Calc video, and we're going to be looking at the first problem set of the derivatives unit, which is focused on the definition of the derivative, or the two different definitions of the derivative, and applying basic knowledge of this new thing that we're calling the derivative. Name drop that word, that vocabulary word, so many times. So we're talking about slope, we're talking about how you can derive it, and how you can connect it to the limit. So without further ado, let's jump into the first of these videos, or the first of the problems. Okay, this takes us to the first problem we're going to attack, and it is literally number 1 in this assignment. So in this first section, I believe it's the first 4 assignments. Let's see, do I have it somewhere? Yes. The first 4 questions we're going to be working through, and we're going to be asked to use one of the definitions of the derivative. Then in the second set of 4, we're going to use the other definition of the derivative. So in this case, it says compute the value of f prime of c for each function at the specified x value using the quote-unquote alternate definition of the derivative. F prime of c equals the limit as x goes to c of f of x minus f of c over x minus c. So before we jump in, it's worth reminding you where this is coming from. So I'll just do a quick little illustration of the picture of what we're talking about here. So we've got some function f of x. There it is. And what we want to do is we want to figure out what is the slope, or even later the equation of the tangent line at that point, which we're going to call c comma f of c. The thought process being it's at x equals c, and the y value that it's at that point would be f of c. So we want to know what the slope is of this line. So we're basically looking for that value m. In order to do that, what we do is we choose another point that's somewhere nearby, and in this case, we're going to call that point just a general point x comma f of x, because it's just another point on the line. And what we're going to do is we're slowly going to take that point. Let's see if the computer will cooperate with me. Oh, it does. We're going to slowly bring that point, not that way, right? That was wrong. We're going to slowly bring that point. Oh, it doesn't want to cooperate. My pen's not strong enough. Whatever. We want to slowly bring that point closer, so that way we can turn what would otherwise be a secant line slowly into what is effectively a tangent line. So that's our goal. So in a sense, in order to do that, if we want to figure it out, what we need to do is we need to calculate the slope the old-fashioned way. We say that m, in the old-fashioned place, was going to be approximated, because again, we're trying to get the slope of the tangent line. It's going to be approximated by the slope of that secant line that goes through right there. Sorry, I didn't do a good job, but right there. That slope would just be, of course, y2 minus y1 over x2 minus x1. But in our particular point, those values are f of x minus f of c. And again, what I'm doing is I'm going y2, y1, and then of course x2, x1. So that's our change in y. And again, if you'll recall, that's just change in y over change in x. Down below we'll have x2, which is x, minus x1, which is c. And so this would normally be our approximate value of the slope. But if we want to know the exact slope of that tangent line that we're looking for, we can find that exact value by imagining those points getting closer and closer, which in other words means that we want to take that x value, and we want to evaluate the limit as it approaches the c value where we're interested in finding the slope. And voila, we have what's called the alternate definition of the derivative, that returns the slope or derivative at a particular point on a function f of x. So in other words, all we need to do if we want to compute the value of f prime of c here, which is our notation for this specific slope that we're looking for, all we need to do is set up the limit of the difference quotient that you see right up here. And again, this is called the difference quotient. I don't want to write DQ because that makes me think of either disqualification or Dairy Queen. But we take the limit of that difference quotient, we make it into the slope of a tangent line, or an instantaneous rate of change. So in here, first thing I want to do is get this thing set up. We got a parabola, and we're talking about x equals 3, which means for our sake, we're trying to find f prime of 3, just as a heads up. In order to do this, we want to evaluate the limit as x approaches 3, because again, that's our c. We want the limit as x approaches 3 of f of x minus f of 3. So because we want to plug in our c value, it's going to be 3 squared minus 3 times 3 all over x minus 3. So this is the limit that contains our slope value. This is going to be equal to f prime of 3. So let's see if we can simplify it. Well, a couple nice things here. I noticed that this is going to go to 0. So really, this is just the limit as x approaches 3 of x squared minus 3x over x minus 3. And for the record, that numerator factors nicely. This isn't even a difficult trimming the quills kind of problem. You can factor out a GCF of x and be left with x quantity x minus 3 divided by x minus 3. And oh look! Divide away. That means this limit is equivalent to the limit as x approaches 3 of x, meaning that x, of course, agrees with the original function, or the original difference quotient at all points. And, of course, that is equal to 3. Voila. There is our slope at that particular point. And again, although we're not going to focus on Desmos here, it's worth pointing out as we pull this puppy up. So we take a look here. Our function was f of x equals x squared minus 3x. And by the way, if we want to find f prime of 3, it says that value is 3, just like what we found. So good job, us. There's our first one. Okay, the second question we're going to look at from this section, I think it's the last one we're going to do together here, or we're going to do in this video solution, is asking us to do the same thing, but with the function 11 over x squared at x equals 2. So again, playing along with the notation here, what we're looking for is f prime of 2, which represents the slope of the tangent line at x equals 2. So a couple little things here as we start to dig into this picture. So 11 over x squared, by the way, looks a little something like this. Some would call it the volcano. I've always been a big fan of anteaters, so I see kind of the anteater look right here. Favorite animal at the zoo, at least the Sacramento Zoo. So that's what we're looking for. There's 11 over x squared. X equals 2 would be somewhere over here. So although my picture isn't perfect, I'm expecting the slope that we get out to be some sort of negative value. So again, I'm just using a graph to kind of help build some intuition about what we're looking for. In fact, as you get further and further into this, you don't necessarily have to draw that out, but you might think about it in your brain and just kind of picture and kind of anticipate what's there. It's the sort of like calculus sense ideas that really can pay off later on. So there is that graph in my brain. So I want negative slope here. So I want a negative number out of this. Okay, next, jumping in. We want to use the alternate definition of the derivative because we're asking for a specific value there. And you were supposed to use that definition. It's going to be the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So, evaluating the expressions that we have in question, we're going to have f of x, which is 11 over x squared, minus f of 2, which is 11 over 2 squared, or 11 over 4. And I'm going to save myself a little bit of writing here. All this will be over x minus 2. Now, as I look at this expression, it doesn't look like it's ready-made to simplify for me. So I'm going to have to, find some common denominator and stuff. So I'm going to multiply up and down by 4. I'm going to multiply up and down by x squared. You know what? I'm going to do this in a different color. What the heck? I'm sitting here. It's the 4th of July for the moment. Let's do this. Multiply by 4, multiply by 4, multiply by x squared, multiply by x squared. So in a sense, what we're doing is we're getting a common denominator. It's now going to be the limit as x goes to 2 of 44 minus 11x squared divided by 4x squared divided by x minus 2. So pulling this down a little bit, we can rewrite our limit. Got a couple different moves I'm going to make here. So if you've watched the video solutions before this point, especially in the first unit, you'll know that when you have a over b divided by c, that ends up being a over b divided by c, which is a over b times 1 over c, which is a over bc. This is a shorthand way of saying I'm going to crunch all this stuff together. So specifically, this will be 44 minus 11x squared, which we're going to factor in just a second, don't you worry. The denominator, will be 4x squared x minus 2. And now it's time to simplify what we can. That numerator, I'm going to pull out a GCF of negative 11. It's going to leave me x squared minus 4. If you don't trust me, multiply that back through and see what happens. Oh, yep, there it is, told you. And then in that numerator, we can clean that up a little bit more and see the factor we're trying to get rid of. And by the way, I should have pointed out that I should have tried direct substitution and seen that we did in fact get 0 over 0 early, but we did. It's always going to come out that way in these difference quotient problems. Otherwise, you're making a mistake. So I'm looking at what we have here. The x minus 2's divide away. I can do that in a single swoop. They divide away. That means we're evaluating the limit as x goes to 2 of negative 11 x plus 2. I like that there's a negative there. Remember, we said to anticipate a negative slope. In our denominator, we just have 4x squared. So plugging in 2, we're going to get negative 11 times 2 plus 2 over 4 times 4. That's going to be negative 11 times 4 over, watch this, 4 times 4. The 4's can divide away. We end up with the slope of negative 11 over 4. And voila, there's our stuff. And once again, we can go check in the computer if we got the, or on Desmos, if we got the right value. I'm seeing negative 11 fourths. We have 11 over x squared. And we were trying for f prime of 2. It says negative 2.75. 11 over 4 is, of course, that same value. So in fact, we once again found the value that we were looking for. So good job, us. Okay. That brings us next to question number 7. 7 is from the second section that asks us to use the alternate definition, or the original definition of the derivative. We just didn't start there for simplicity. So this is for the general derivative, meaning that instead of getting the slope at a single point, we want to get a function that describes the slope at any particular point. Our starting kind of origin story for how this works is the same. Actually, I'm going to draw it this way. We're going to be the same way that we started before. The only difference is we're not going to lock ourselves at x or c comma f of c. We're going to lock ourselves at a general point x comma f of x. And then we're going to choose a second point to play with. And that point is going to be h units away, which we're going to say is x plus h. So that way there's a difference or a separation of h units between those two. That means this coordinate will be x plus h comma f of x plus h. And that means what we want is to find the slope between those 2 points. Well, the slope of the tangent line at x would end up giving us a slope of f of x plus h minus f of x over x plus h minus x. And if you simplify that, of course, our numerator does not change. Our denominator can be cleaned up nicely to h. And then, of course, if we want the exact slope, or a slope function in this case, I'm just going to call this f prime of x, the slope function. This would be the slope at any x value on this graph, or in the graph's domain. We'd evaluate the limit as h goes to 0. In other words, as we make that distance between those two x values smaller and smaller. So that's our approach here. These are typically a little longer to work through arithmetically or algebraically, but you're doing the same thing that you would otherwise. So let's jump into this first one, huh? Let's do it. So in here, we want f of x equals 12x, and we're looking for f prime of x. We want the slope at any x value, so we could quickly identify what that tangent line slope would happen to be, or what the slope would be. So in here, looking at everything, I'm going to start by just filling this in. We want to evaluate the limit as h goes to 0 of f of x plus h. So we need to take 12 over x. We need to evaluate it at x plus h. So that means we've got to plug in x plus h anywhere where there's an x. So instead of 12 over x, we're going to have 12 over x plus h. Then minus f of x, which is just minus 12 over x, all over h. That's actually a pretty easy denominator. So now once again in here, I'm going to show some stuff. I'm just going to do it with a different color and switch back. We need a common denominator. So I'm going to multiply up and down by x on the first term. I'm going to multiply up and down by x plus h on the second term. When I do, I'm going to get the limit as h goes to 0 of 12x minus, let's see here, I'm going to do an old Miss Nakamura trick, plus the negative, distribute that in, going to be minus 12x, minus 12h. My denominator now has to include both x and x plus h, and then everything is divided by h. Cycling back down around, we now want to simplify this as much as we can, so a couple moves here. First, of course, it's still the limit as h goes to 0. Again, we're shrinking that horizontal distance between the 2 points to turn that secant line into a tangent line. Our numerator has 12x minus 12x minus 12h, so our numerator is negative 12h. Our denominator, I'm going to combine the two denominators together. We just talked about how that works on the previous one. That'll be x plus h times h. And now notice, hey, h over h. So divide those things away. we'll get the limit as h goes to 0 of negative 12 over x times x plus h. We can plug in h equals 0 now. We'll get negative 12 over x times x plus 0. That's going to be equal to negative 12 over x squared. So we were looking for f prime of x. F prime of x turns out to be negative 12 over x squared. And what that means is if we want to know what the slope is at any particular x value on the graph of 12 over x, that slope will just be the x value squared and then negative 12 divided by it. So pretty powerful thing. We now have the slope function for this particular function, which again we call the derivative. So cool stuff. Again, you can kind of see this was kind of a medium to higher level. This is kind of an above average difficulty question. So you can see just a little bit of algebra in there, but not the worst thing in the world. It goes pretty quickly for sure. Okay, that brings us to question number 8. Same exact approach, same exact style, same style question. Only difference is this time we've got a radical function rather than a rational function. So to start things off, I'm just going to dig in. I'm going to plug it into this difference quotient. So this is the limit as h goes to 0. Again, with h being that horizontal distance, h for horizontal distance between the x values. From there, we've got f of x plus h. So once again, we need to take 4 root x, and we need to evaluate it at x plus h. That's going to end up being 4 square root of x plus h minus f of x, so minus 4 root x, all over h. So in here, before I start to dig in and start to work, like I really can't simplify anything as is, so we need to dig in into our trim the quills bag of tricks. In particular, I see square roots, which tells me what I need to do is I need to multiply by the conjugate. So I'm going to multiply by exactly what is in the numerator. 4 square root of x plus h, 4 root x. The only difference is instead of a minus, I'm going to multiply by the conjugates with a plus. And of course, if I do it in the numerator, gosh darn it, I got to do it in the denominator as well. So there's our work. Now it's time for us to simplify this thing. Again, things get worse before they can get better. Sometimes happens. So as far as pieces, we're going to end up with, and I'm going to be really careful here because this can be easy to algebraically mess up. We're going to get 4 root x plus h squared minus quantity 4 root x squared. All of this is over the mysterious and magical h times that conjugate factor we multiplied up and down by. I'm having a hard time not writing that square root to start. So now it's a matter of simplifying what we have. So in our numerator, this will be the limit as h goes to 0 of that same denominator. Out of curiosity, can I be lazy? Yes! Heck yeah. Got to be a little lazy. Got to save myself a little bit of writing. There's our same denominator. Our numerator becomes 16 x plus h minus 16 times x. And if you distribute that out, I'm hoping you'll trust me that we're going to get 16x plus 16h minus 16x, meaning that this entire monstrosity, should I do that extra algebra step? Yeah, I can. 16x plus 16h minus 16x all over, hey, look what I found. And of course, that zeroes those guys out. Means we end up with the limit as h goes to 0 of 16h over h times that thing down there. So looking in here, of course, if we were to try to use direct substitution, you'd see that you get 0 on top and 0 times stuff on the bottom. So this would, of course, be indeterminate. But we don't even have to go that far. Do you notice? In fact, I'll even pull up a different color just to emphasize it more. Have you noticed that there's an h in the numerator and an h in the denominator? That means that our limit is actually the limit as h goes to 0 of 16, which by virtue of never being 0 is now no longer going to be an indeterminate. In our denominator, we have 4 root x plus h plus 4 root x. So in looking at our ingredients in here, there's a couple things. By the way, I don't know if you realize this, but we could factor out a 4 divided by the 16. But you know what? We'll just wait. This is going to be 16 over 4 root x plus 0 plus 4 root x, because of course h is going to 0. That's going to be 16 over 4 root x plus 4 root x. That's going to end up being 16 over 8 root x. And of course, that's going to be 2 over the square root of x. So after all of that, we found that our derivative, f prime of x, is equal to 2 divided by the square root of x. Dunzo. So there is another one. You've seen both of the two, I'd say, algebraically challenging questions in this section from 6 to 8. 5 to 8? 5 to 8. That ask you to use the traditional definition of the derivative. But again, I think you're prepared for this, and you already mastered trimming the quills in the first unit. So there we go. There's number 8 complete. Okay, next, this brings us to questions in the third section. And these questions don't actually ask you to finish any problems. They're not expecting you to actually know the answers to any of these. Instead, they just want us to prepare for something that assesses the skill later on. So in fact, this is typically on the standard quiz. And I believe it is again, but I don't remember the question number, so I'll hold off for now. It says, to identify the function f of x whose derivative is being calculated by the given limit of a difference quotient and the x value at which it would be computed. So they're asking us for two things. They want us to identify the function f of x and the x value at which it would be computed. So in other words, they want to know which function and at what point are we calculating the derivative. So with this in mind, before we jump in, it's worth reminding you that to approach these, you're basically using derivative identities in a sense. So you've got to remember the two definitions of the derivative. We have the alternate one, the limit as x goes to c, of f of x minus f of c, all over f of c, or x of x minus c. Or you've got the traditional definition of the derivative, which is when that horizontal distance between points shrinks to 0. And in this one, the difference quotient is f of x plus h minus f of x, all over h. So what we want to do is we want to first figure out which one of these are, because that's going to help us find f of x, because f of x falls in two different places each time, and the c value might fall in a different spot as well. So in order to do this, the first thing I want to do is I want to try to match these two. So I want to match these things up. So the best way to tell which one's which, or which one you're staring at in a situation like this, is to look at the denominator. One denominator is x minus a number, and that number, by the way, happens to be the value we're trying to calculate the slope at. And the other one has an h in the denominator, or delta x, or something like that. Looking over at our function, I see x minus 8. What that tells me is that this is going to be equal to the limit as x goes to c of f of x minus f of c, all over x minus c. So with that in mind, if we want to find f of x, we need to look at the front. So I see ln of x plus 42 minus ln of 8 minus 42. That tells me that f of x, the function whose derivative is being calculated here, is going to be ln of x plus 42. Again, it doesn't matter that we don't know the derivative or we couldn't evaluate this by hand. Just that's what we were looking for. And then we're going to be evaluating it at x equals c. Well, c is down there, also right there. Also plugged into the function, I see 8, 8, 8, which tells me this is probably going to be at x equals 8. So in other words, it doesn't ask this for us, but this is basically asking us to find f prime of 8 for f of x equals ln of x plus 42. So there's our first one. And again, we're not evaluating yet. On the standard quiz, you will have to evaluate, but we just don't know any tools for evaluating derivatives just yet, so we have to kind of hold off for now. But there is 10. Okay, that brings us next to question number 12. I think number 12 just looks the worst. I don't think it's that much more difficult than the previous problem. It asks us to do the same thing here. So a good place to begin would be to recall the two different, like difference quotient derivative. Oh, what happened there? There it is. The two different forms that we have. So keep in mind that was what we were given. Nope, it didn't take that line with it. Let's draw that in there. Cool and close enough. So looking in here, which one looks more right? Well, once again, let's look at the denominators. X minus c, no, it's just an h. That tells me we must be looking at this one. So that means that we've got an f of x plus h minus f of x. So in other words, our function must be over here. The only difference is, I don't know if you've noticed this, but instead of x plus h, we have 1 plus h. And instead of something with an x in it over on the right side of the numerator, we have 3 times 1 squared. My theory is that that means f of x is going to be 6e to the 3x squared. My thought process is if you replace that 1 with an x each time, you'll end up getting what you were looking for. Now it fits that f of x plus h minus f of x over h form that we were looking for. So I think that's f of x. Only downside is that we also need to figure out at what x value we're talking here, but I think we just solved it. If we have x as 1, or if we have 1 plugged in, that's just the x value we're looking at. So I'm going to say that this is the function 6e to the 3x squared, and it's being evaluated at x equals 1. So there's our answer. Or you could say that we want f prime of 1 for the function f of x equals 6e to the 3x squared. So again, not particularly difficult, but this is all about like structure. You're seeking structure in every single one of these problems, trying to identify what is the function whose derivative is being like set up here so that we could derive it and work our way through. And by derive, I mean using known results, not a word for differentiate. Once again, there is number 12, nothing particularly crazy, just a little bit of looking, and again, looking for structure. Always trying to find structure in what's there mathematically. Okay, last but not least, the final question on there. As I said before, this is a pretty straightforward, quick assignment. The last question is from the final section of the assignment. It tells us to determine whether the derivative would be positive or negative at the indicated point. No work is necessary to show for these problems, but of course, I'm the person who writes an essay to answer a single true or false question. So here we go. There's our picture. The point in question is right there. And if we're talking about the derivative, we should know, or you should know, or you should be getting used to knowing, you should be willing to fake knowing until you do know it, that derivative is just a fancy way of saying slope. The same way Grey Poupon is a fancy way of saying mustard. Which is gross, I don't like mustard. So derivative is just slope. So we're talking about the slope. So the question is, what is the slope at that point? Well, if you're not sure, since the derivative is all about finding the slope of the tangent line, you could, of course, draw the tangent line on the graph. There we go. I just drew the tangent line. Could even give it a tangent liney name like t of x. So at that tangent line, the derivative, f prime of x, assuming this is, of course, f of x, the function, tangent line's t of x, f of x is that, the derivative, f prime of x, is equal to the slope of the tangent line. So the question that you need to ask yourself, in this case, I gotta write tan line, middle of summer, you could get sunburned. Slope of the tangent line. The question you can ask yourself is the slope of this particular tangent line positive or negative? And I think you can clearly see that the slope of that tangent line is negative. So that tells me that the derivative at that point that we were interested in, like the slope of the thing, because it literally is the slope of the function at that point, that slope is negative, so the answer to our question is negative. Had we chosen a point, say, right over here, that slope, it's hard to draw this, that slope would have been positive because it has positive slope. So there we go. We'll also talk about all sorts of other ways to identify positive or negative derivative and stuff later. But for now, that completes our videos from the work on the defining the derivatives assignment. Hopefully this has clarified a few questions for you and put you in good position to nail every section and to understand everything when we jump in to start going a little bit faster tomorrow. Have a great night, and thanks for watching.